Okay, welcome to Chapter 11, talking about modern atomic theory. This is probably going to be one of the more theoretical chapters that we will go through, but an understanding of this will help you to understand why atoms interact with other atoms the way that they do. So we're going to begin with a review of Rutherford's experiment, sometimes referred to as the gold foil experiment. And what he did is he shot alpha particles in the direction of a thin, very thin piece of gold foil, and part of his expectation is that these would go through, but what he didn't expect is that it would bounce off. And this proved that there was a dense center of positive charge, and that dense center of positive charge a few years later was understood to be protons and neutrons in the nucleus of the atom. So a dense center of positive charge. Since neutrons have no charge, the nucleus of the atom is extremely positively charged, and they figured out that the electrons are somewhere around the outside of the atom. So when you have positives and negatives, opposites attract each other. And what they couldn't figure out is why these electrons were not falling right into the nucleus, why they weren't attracted into there, because opposites are supposed to attract. And the atom, actually, they understood the electrons to be outside of it. So to understand how they began to understand the structure of the atom and what the electrons were doing, which is the key to chemistry, we need to recall some key points about the nature of light and how it transmits energy. And what we're going to do is take a look at some of the specifics of how light operates and understand that there's a relationship between light and energy. So to make it simple, let's use the analogy of the sun. The sun is shining down, and during the daytime you can feel the warmth of it if you're out during the summertime. Okay? So we understand that heat is energy, that light is coming from the sun, and that light is actually giving us energy. Well, all energy is known as electromagnetic radiation. Electromagnetic radiation comes in very high wavelengths, such as very high frequency, such as gamma rays, X-rays, and they come in very harmless types of things like radio waves or television waves. So even as you're sitting right now listening to this, you are getting bombarded by radio waves and television. You also get your cell phones giving off energy to you, and all of these things are hitting you even if you're in a dark room. You want to stay away from high energy, and so the X-rays can give high energy, and they tend to do more damage to cells of people. So we don't want to be exposed to those too much. For example, your dentist takes X-rays of your teeth, and he puts a little lead shield on your chest, and then he steps out of the room. That should be a warning sign that this is dangerous. So what I would like you to do is to answer the following questions, and I know that you may not know all the answers to them, but give your best answer looking at the drawings above. In other words, to answer what type of electromagnetic wave has the highest frequency, you can see that answer above. And then some of these are just simple questions based upon what you may or may not know. And once we're in class, we'll check those answers and see how you did on that and make sure you understand all of those. So what I'm going to do is try and draw a picture of just the visible light spectrum, because this is something that we will use when we're together in class to understand light waves and energy. But you can look up above and you can see that what I'm writing is correct. So, not being a great artist, you'll have to forgive me, but I am going to start here at the violet end, and these waves are relatively close together. And as you go farther and farther down, the waves get farther apart. So over here, you have high frequency, and chemists used the Greek letter lambda to indicate that. So you're kind of making a V, except you go down and then you curve up and back. So these are high frequency, they are high energy, but they have a short wavelength. And wavelength, we use the Greek letter lambda. So this is lambda. It stands for the wavelength. So the wavelength is typically taken from peak to peak. So the shorter the distance, we say that is a short wavelength. If you come over to the red side, they're farther apart from each other, and it has a long wavelength. It has low frequency, and it also has low energy. And let me write that up here. Sorry, having a couple of problems with my pen here. So, low energy. So whenever you see the red light, I want you to think of that in terms of something that doesn't carry a great deal of energy. And then you have the visible. What's on the other side of the visible, or I'm sorry, of violet light, is ultraviolet light. And I'm sorry, I didn't say it, but Roy G. Biv, these letters up here, stands for red, orange, yellow, green, blue, indigo, and violet. Officially, indigo has been dropped. I don't quite know why, but they decided not to include indigo, but it's easy to remember Roy G. Biv. So when you see red light, that's a very low energy light. A violet light is a very high energy light. And so when we're in class, I will do a little demo and show you some of the colors that are given off by elements and talk about whether they are high energy or low energy. Now the question is, light can behave as both a wave and as a particle. So as a wave and a particle, light has what we call a dual nature. In our Christian faith, we also say that Jesus has a dual nature, and the dual nature of Jesus is that he is both man and God. He is fully man and he is fully God. It's hard to explain that, but it's also hard to explain how light can be pictured both as a wave and a particle. A wave carries energy but has no substance to it. Particles tend to have mass and are limited in regards to how fast they can move. And we need to understand this because the nature of light is going to reflect what happens with electrons in atoms. So when we're together, I'll do a little demonstration of burning salts. And just so you get a little chemistry language down here, a salt is a combination of a metal and a nonmetal combined together. So you know the salt NaCl. Well, sodium is the metal, chloride is the nonmetal. But chemists use this in all sorts of ways, so we would say magnesium sulfide, MgS, is also a salt because it contains a metal and a nonmetal. So we will get to the demonstration when we're together in class and we'll answer some of the questions that are here. But if an electron receives energy from an outside source, so let's say it's hit with a burst of energy, it is going to gain more energy. It's going to be energized. Just like if you were standing still and somebody pushed you, you would have more energy because you would have kinetic energy from getting pushed by somebody else. Electrons do the same thing. And we say that when they gain energy, they move to what is called an excited state. Yes, that is a technical chemistry term. And then, when they give up that energy, they return to what is called the ground state. And so the excited state is when they have taken in energy or absorbed energy. And then going back down to the ground state, they actually release energy. And that release of energy sometimes happens in regards to a visible wavelength of light, or a specific wavelength corresponds to a specific color of light. So when we say that we can describe light as both photons and waves, a high energy photon is talking about light as a particle. It's acting like little massless bundles of energy that are just going along. And we can also talk about that color coming out as a particle, i.e. a photon, or we can talk about that color as a wave. And we can assign to it a specific wavelength and frequency. So the wavelength, once again, are the peaks, and the frequency is within a given distance, how many wavelengths have actually passed by. So that's going to be your frequency, and the distance between the peaks is the wavelength. Okay, let's go on to this topic called spectroscopy. And when we're together in class once again, I'm going to show you some demonstrations of what scientists actually saw that allowed them to understand what is going on in the atom with regard to the electron. And the results of this will be that we will understand how hydrogen was shown to demonstrate specific arrangements of electrons around the nucleus of the atom. So recall that I said that an atom with excess energy is said to be in an excited state. And that excited atom can release excess energy by emitting a photon, and that allows the atom to return to its ground state. The ground state is the lowest possible energy state of the atom. That's where all atoms like to be. Very similar to a man on Sunday. He likes to be in the lowest energy state so he can watch his team play football. So let's take a little picture of what happens in an atom. Here's the nucleus of the atom, and here is a picture. This is called Bohr's model of the atom, and there's electrons in the energy levels. Okay, and since we're talking about hydrogen, I have to erase some of the electrons because there is only one electron and one proton in hydrogen. So what happens is when energy comes in and strikes that proton, or I'm sorry, not the proton, but the electron, that electron is going to absorb that energy. So in the excited state, here's what that looks like. The electron was here, but it goes to a very specific spot. So I'm drawing rings to show that there are only certain places that this electron can go. It can't go wherever it likes. So it jumps out to that third ring. And now the electron is out there. So let me try to erase the previous spot of the electron, which I realize you can't do. And I'll draw the ring back in. But the electron has now been promoted to a position further away from the nucleus. That is called the excited state. And then that electron and I won't erase again here, that electron is going to return to the ground state. So when it returns from here to here, so the electron right there, it lets out a certain wavelength of light, and that relates to a color or a wavelength, and a wavelength relates to a frequency. And frequency means energy. So when the hydrogen atom emits a photon from its excited state, it only emits photons of certain discrete energies. These are specific wavelengths or frequencies. These are caused by what we call quantized levels. And this is a technical term I do want you to remember. A quantized level is specific areas around the atom where electrons are allowed to go to. So the Bohr model of the atom, once again, it's kind of like a target symbol. You've got the nucleus and you've got these rings that go around the atom. And another way that I'm going to draw this is to say, okay, this is the nucleus here. And this far away is the first energy level. That's the first place that electrons can go. It cannot stop anywhere in between. It has to go up there. It can also go to another place a little further above, and that's called the second energy level. Very creative names, I know. Sorry, I misspelled energy. And then a little bit further up, but closer than the last jump, is the third energy level, and that goes on and on and on. Okay? So I can use either one of these pictures to actually show what happens. The important thing to realize is that this is called quantized. So if I were playing tennis, scoring in tennis is quantized. If you know how to play the game, when you score, you start out at 0, or what they call love. And then you go to 15, 30, 40, and unless you're caught in a little deuce advantage situation, you're going to win the game on that next point. So this is quantized scoring. There's only certain specific numbers that you can get in a tennis game. But if you're playing basketball, you could score 1 point, 2 points, 3 points, or you could score 2 points twice and get up to 4, or 2 plus 3 and get up to 5, or 2 plus 3 plus 1 and get up to 6. You're going to hit every whole number on the way. So in basketball, there is not quantized scoring. They can have a score of 16-3, and you would never have that in tennis. So quantized simply means very specific places that you can stop and have a score, or for the atom, it's very specific energy levels that the atom can appear at. So if these very specific energy levels did not exist, we would see colors of all sorts. Okay, what do I mean by that? Well, if you take visible light and you put it into a prism, you can break off all the different colors of visible light. Okay? So you're going to get your red, orange, yellow, green, blue. And when we do it with an atom, we are not seeing every color of light. We're only seeing very specific wavelengths of light. We're seeing certain colors only. So if we had every color of light available, what we would see would be a combination of all the colors, which is just simply white light. And we don't see that, we only see certain colors. Therefore, we have scientific evidence that the energy levels of an atom are quantized energy levels. Very specific places only are allowed. All right, let's go back to the Bohr model of the atom. And Niels Bohr won the prize, the Nobel Prize in physics, I think it was, back in the early 1900s for his model of the atom. And it did explain hydrogen perfectly. Hydrogen has one electron only, but it's not entirely accurate because electrons don't move in orbits. And this was kind of the question that Niels Bohr was trying to address. If the electrons don't fall into the nucleus, what are they doing? They are simply orbiting around the nucleus, just like the Earth orbits around the Sun. So the whole idea of orbits came about because of Bohr's concept of the atom. Mathematically, he had calculated where this ring was, distance-wise from the nucleus, where this ring was, where this ring was. But the problem is electrons don't move in orbits around the nucleus of the atom. Electrons tend to move randomly, and they come and go as they like, but they tend to stay right around the nucleus. But his model was very useful because it demonstrated quantized energy levels, and not only quantized energy levels, but it also correctly predicted the colors of the hydrogen electron as it went from one energy level to another. So his math was perfect, but it only worked for hydrogen and no other polyelectronic atoms. Polyelectronic just means many electrons. Okay? So it worked for hydrogen, but not for other elements at all. And this is where we will end our first video, and we will pick that up later on. Thank you.